All right, everyone, we're going to get started. So please join me in welcoming Dan Goldberg, who's joining us today from the Milken Institute School of Public Health at George Washington University, and also representing Argonne National Lab. Dan got his master's and PhD in atmospheric and oceanic sciences from the University of Maryland, and followed that up with a postdoc at Argonne. He mainly studies the public health impacts of air pollution, and in particular combining satellite observations, including TROPOMI, with models and in situ observations to gain insight into city and exposure scale chemistry and its impacts on public health. So today he's going to talk to us about estimating NOx emissions from global cities using satellite data. So Dan, welcome and take it away.
Thank you, Nick. It's a real pleasure to be here. Good afternoon to everybody. I'm very happy to present, and I'm glad that I can do this virtually. I don't have to even leave my house. First of all, the presentation can be downloaded either at the link shown in the front center of the slide here, or also in the Slido. There's a link directly there. So I encourage you to check out that version. It's a PDF version. It has all the links to the papers and any other information that you might be interested in seeing. Also, I'm actually thrilled to be at this particular seminar due to your division director, Peter Nelleveld. She's a big champion of satellite data, and I'll be presenting very heavily using OMI data and TROPOMI data. So today I'll be discussing or estimating NOx emissions from global cities using satellite data. And as Nick mentioned, I'm at GW and Argonne National Lab. All right, getting to the presentation. So why is NO2 by itself an important air pollutant? I'm not even considering the effects of NO2 in formation of ozone and PM 2.5. Those two pollutants are obviously very clearly adverse air pollutants, but NO2 by itself impairs cardiovascular function. It also causes and exacerbates asthma. Susan Annenberg and postdoc Ploy Achek-Kulisek published a paper showing about 4 million children developed asthma per year, and this is entirely preventable cases of asthma if we had less NO2 pollution. That presumably or hopefully we get that number down close to zero. NO2 is also co-emitted with other harmful pollutants such as diesel PM, VOCs, heavy metals. It also contributes to acid rain and impairs natural visibility. Here's a snapshot recently from Rogine at Columbia University, who spoke, I believe, last week. And this is showing that NO2 is still a problem in New York City. NO2 was 50 ppb on this particular day. And you can see the brown cloud in downtown New York City. So what does NO2 satellite data look like? Here's a 20-month average for the Denver region. I like to take a local snapshot of wherever I'm presenting. And you can very clearly see that NO2 pollution is worse in downtown. It's actually the Highland neighborhood. It had a value of 6 times 10 to the 15. And these units are molecules per centimeter squared. It's a bit funky, but for those who aren't as familiar, red is large, blue is low. That should be fairly obvious. But NO2 can also vary quite a bit on day to day. So here's a snapshot, actually one of the most polluted days in the last 3 years. And this was October 15th, 2019. And on this particular day, you can see very clearly NO2 pollution along the foothills. And I'll change the color bar here. It's actually now 2.5 times larger on the right side. And you can see, yeah, the pollution is close to 20 times 10 to the 15. So at any individual day, NO2 pollution can still be quite a big problem. But of course, I know this is a virtual seminar, and not everybody is located in Colorado. And so I'm here showing the entire continental United States, and again, a 20-month period. And unsurprisingly, the worst NO2 pollution is in East Los Angeles, or essentially downtown Los Angeles. But close behind is Brooklyn, New York City, and the port of Newark, New Jersey. All three have very large values. But what's also remarkable about this image is you can very clearly see lots of different point sources. You can obviously see lots of different cities. And we can also quantify where the largest and the largest, but also the cleanest parts of each state are. And so now going through the cleanest parts of each state, or cleanest states, actually Vermont appears to be the cleanest state, followed closely by South Dakota, Mississippi, Maine, and New Hampshire. So interesting kind of tidbit that I want to start the presentation with. For this presentation, I'm not actually going to discuss any of my work on the COVID lockdowns. I actually included a 3-minute video. Again, you can, if you want, you're interested in that video, check out the PDF version, which has the hyperlink to it. All right, so how is NO2 data measured? And here's a quick secret, is that measurements actually need model information. So there's 3 general broad steps to quote unquote measure measure NO2 from satellite data. The first thing is you measure the radiances in the approximately 400 and 450 nanometer range. It's approximately indigo. And this is used to create a total slant column between the detector, which is at approximately 700 kilometers above us, and the ground surface. In the next step, this is, you want to separate the stratospheric component from the tropospheric component. There's 2 different methods that you can do this. Some algorithms use a model, and some use a clean measurement over the Pacific Ocean. And then in the third step, we use information from a radiative transfer model and a chemical transport model to calculate an air mass factor, which I'll discuss more in a second. And this air mass factor is used to convert a slant tropospheric column to the vertical column. It's important to note that steps 2 and 3 can be large sources of uncertainty, and especially step 3. So that's what I'm going to discuss in the next slide. So what is an air mass factor? Those familiar with satellite data probably have heard this term before, but people who haven't looked at satellite data before, haven't really utilized satellite data much, perhaps don't know what this is. So it's approximately a value between 0.5 and 2. It's unitless, and it's simply the value used to convert the slant column into a vertical column. On the right, I'm showing that identically, but there's a very long equation, a long methodology to actually derive what the AMF is. And it's a function of a lot of things: the instrument viewing angle, the solar zenith angle, the surface pressure, clouds, surface reflectivity, and I won't say most importantly, but this is what I'll discuss, is the a priori vertical NO2 shape profile. If you want more information on the air mass factor and you really want the nitty gritty here, check out the 3 references I list there in the bottom right. And so how is the air mass factor derived, in particular related to the vertical shape profile? So on these 3 plots on the left here, I'm showing the vertical profile in Baltimore, in the location of a power plant just outside Baltimore, and in a rural location just west of Baltimore. And we can see that first of all, the X axis is a log scale, and we can see that GMI, which is the NASA global simulation, estimates free tropospheric NO2 at approximately 100 ppt or 0.1 ppb, whereas CMAC is about 5 times smaller than that. Conversely, near the surface, CMAC has, at least in Baltimore, simulates a concentration of 10 parts per billion, more or less, and the blue which is the global model, simulates only about 2 ppb. In the black triangle there, hopefully you can see that it shows that the actual observations in downtown Baltimore are fairly close to 10 ppb. So we're using, what I do is I use information from this regional chemical transport model to recalculate the air mass factor. And this is probably the most complicated slide of this presentation. And so you essentially multiply the scattering weight, which you can see there in the green, times the shape profile, and you get this air mass factor. The full equation is the top right. And more or less, the air mass factor is representative of the area underneath the blue curve. So the area to the left of the blue curve. And for the operational product and for the this new regional product is the area underneath the red curve. And we can see that the area underneath the red curve is significantly smaller, especially in the Baltimore case and also the power plant case. So because of this, because the air mass factor should be smaller, again, the observations show that the regional model is doing a better job. The operational tropospheric vertical columns are going to be too small in polluted regions. This is actually fairly well known in the community, but it's still important to demonstrate this and quantify this. And so I know several of you are modelers. Not all models are perfect, but some are useful. I'm sure you've heard that many times. And the shape profile is quite key. Regional models are generally pretty good, but they're not always the best. And in particular, for whatever reason, I found that global models do a better job with the free tropospheric NO2. It's still unclear why, but most importantly, the regional model must have lightning knocks. And so what I actually end up doing is I use a hybrid approach. Is below 3 kilometers in the atmosphere, I use a regional chemical transport model. Above 3 kilometers, I use a global chemical transport model. And then when observations are available, in this particular paper, I use Discover AQ, Maryland observations. I scale the mean vertical profile to the mean of the observations. In this right panel, you can see that CMAC actually did a pretty good job of matching the observations for NO2. GMI did not do a good job at all. But even around the 2 kilometer height, CMAC is significantly overestimating NO2 compared to the observation. So I scale for that. So this is what I derive what I call is a regional satellite product. And I'll go through the steps here. So on the top left, I'm showing the operational OMI NO2 product. This is operational as of 4 years ago now. So take that with a grain of salt. There's been new products released since then. So the operational is on the left, top left, and then top right. I'm using CMAC with no adjustment whatsoever, just using the standard CMAC vertical profiles to estimate the air mass factor. And we can very clearly see that this yields a measurement that is larger. Then when we go from B to C, from the top right to the bottom left, I then scale the CMAC vertical profiles based on both Discover AQ observations and also Seeker's observations, which were acquired a couple years later, but they are indicative of the free troposphere, which there were no measurements in the free troposphere during Discover AQ. And then finally, from C to D, I just impose the model spatial variability. So actually C and D, if you average across the entire domains there, they're exactly identical. It's just that in D, you can start to pick out variability within cities. And that's because of the model that I'm imposing on the data. So how does this compare to Pandora measurements? So Pandora is an upward-looking spectrometer, and this takes measurements of the total vertical column of the atmosphere. And quite simply, this new regional product does a much better job at matching the Pandora measurements than the operational product. we can see that the operational product does actually an okay job at fairly low NO2 concentrations, but at high concentrations, the operational product is low by essentially 50%. Now, if we contrast that to the regional product, so this is with CMAC with both the observations and downscaled, we can see a slope almost near unity, and in R squared that's better. I mean, there's just going to be a lot of variability, so R squared isn't perfect, but certainly much better than the operational product. So I actually did this exact same thing using data during course AQ, which occurred a few years after, I believe, in 2016. And yeah, did the same thing here. So, and it's really the same type of conclusion, is that the operational product yields values that are too low compared to the Pandora network. In the standard product, I'm showing the Pandoras in the circles here on each plot. And then when we go to the regional product, and then also imply this spatial kernel, we get almost, I would say, a very excellent agreement in the Seoul metropolitan area once you make these two changes to the measurements. So now that I've discussed a little bit what a regional satellite product looks like, or what it is, I'm going to switch gears a little bit and discuss inverse modeling. So how do we actually quantify NOx emissions? So how does inverse modeling work? So the first thing is we really want to take a known quantity, and in this particular case, I'm showing the known quantity as the Four Corners and San Juan power plant complex in New Mexico. Just as a disclaimer, Josh Loeffner talked about actually, I think it's an identical method he used to estimate the OH concentration a few weeks ago. But I'll just go through this method so that everybody is on the same page. So we take the measurements over the power plant complex, and then we rotate that based on the winds. And so we want to artificially have a plume decay from, in this case, left to right, so that you can, the actual emissions are at the center, at the origin there, but the NO2 actually peaks a little bit downwind and then exponentially decays. If I use the operational product, I get a top-down emissions of about 3.5 megagrams per hour and an effective lifetime of approximately 6 hours. However, and so to calculate this is the equation shown right here. It's actually just four parameters. Both the burden and the decay distance are from this statistical fit, which is the light blue line on the slide. The NOx to NO2 ratio is from a model simulation and is 1.32, and the wind speed is from the ERA 5, or actually in this particular case is ERA intern, but I use ERA 5 in my analysis today. But the real key point here is that we want to use this this product with regional air mass factors. So I showed in the previous slide that the top-down emissions were 3.5 megagrams per hour, but the actual measurements were 6.4. So very clearly underestimating the emissions. But when we now use these regional air mass factors, in this particular case, it was from Environment Canada model simulation, we get a top-down emissions estimate of now 7 megagrams per hour, and the SEMs were 6.4. So this is within about 10%, and I would say this is excellent agreement. Ben Defoe has also published several papers on doing sensitivity analyses with this method, and I highly encourage people to check those references out if you're interested in this method. So back to South Korea. Here I'm using the same method, but now instead of a power plant, I'm using Seoul, Korea as the effective point source. I'm not trying to disentangle, any individual source, but just trying to group all the NOx emissions in Seoul together here. And so if I apply this method to a model simulation, I'm not showing that here, but when I do, it's about 360 kilotons per year, which is same as gigagrams per year. And this, using the top-down method, using the operational product, I get a very similar value. But again, we know that the operational product is underestimating NO2 pollution in downtown polluted areas. And so when we adjust the air mass factor, we then see that NOx emissions in Seoul, Korea are underestimated by about 34%, or in other words, the emissions inventory should be increased by about a factor of 1.5. But there's a caveat to this, unfortunately. And that caveat is that the satellite measurement is only in the mid-afternoon. And so actually some fraction of the disagreement is likely related to the diurnal allocations of emissions. And so this is something that is an research interest of mine, and it'd be really helpful to have geostationary satellite instruments, which we actually have one up now in over Korea. So very looking forward to that data. But we can see on the left panel here, I'm showing the diurnal emissions from New York City. This is grouped for all sources together. And this is the 24-hour mean is in the red, and the local time mid-afternoon mean is about a factor of 1.4 larger than the 24-hour mean. And generally the shape of the NOx emissions in New York City is more or less what I would expect, where you get an increase around 8 a.m. in the morning, kind of steadily increases until peaks around 4 or 5 p.m. in the afternoon, then decreases thereafter. However, in Seoul, South Korea, the preprocessor actually said that the mid-afternoon emissions were approximately equivalent to the 24-hour mean. And so this is actually quite a big difference between the two cities. Is this real? Is this not? I mean, I'm not sure anybody truly knows. My personal opinion is that the Seoul emission diurnal profile should look somewhat similar to New York City, but certainly I wouldn't expect it to be identical. I mean, different cultures have different ways of living, different types of energy sources, et cetera. So just something I want to put in the back of people's minds. So this mid-afternoon bias really is something that's important to be aware of. All right, so here's just the seminar summary so far. Tropospheric vertical column measurements actually need model information. These operational vertical column measurements have a low bias in urban and highly polluted areas, and this is due to an air mass factor bias. I would say this can be quote unquote solved. I'm not sure that's perhaps the best word, but it can be modified using a hybrid approach called with using regional models, global models, and vertical observations when they're available. Generally, these regional products show excellent agreement with the Pandora measurements, and we definitely need more observations of free tropospheric NO2. There's really a scarcity of these observations over land, and I'm very much looking for any types of those measurements. And then finally, a remaining question is, what's the true diurnal pattern of NOx emissions? Does it vary by continent? And these geostationary satellites will be key. Surface measurements are tricky to use in this particular instant because the boundary layer dynamics are so, the boundary layer is just so small during the morning, and it really complicates things. So next, I'm going to be using some of these regional satellite products to estimate NOx in cities. So let's take go back to the globe for a second. Here are NOx emissions inventory, 4 different NOx emissions inventories globally. And the bottom right of each panel, I have the teragrams per year of each emissions inventory for the year 2005. And we can see all four of these emissions inventories, the SEDS, the MAC City, the Edgar, and the Eclipse or GAINS, show a total NOx emissions of approximately 110 to 120 teragrams per year. And even still, you really have to squint to see if there's any differences on a regional basis. They look, if I didn't tell you, you might have assumed that these were all four identical plots, but they're not. And so how do these emissions inventories compare on a city scale? And then how well do these emissions inventories capture trends over time, especially in cities? And so here I've mapped out into 10 different regions, sort of by continent, but not identically by continent. I've separated Asia out into a few. And we can see that there's some variability between the emissions inventories, but generally they're all kind of similar with respect to changes over time. The big difference, I would say, would be in China, which is the fourth column, top row. And we can see that the SEDS emissions inventory shows a peak in the 2011-2012 timeframe with a decrease thereafter, whereas the other emissions inventories show an increase. We actually know that there was a peak and it's gone down, but this is just a reminder that a lot of emissions inventories take a long time to process. I'm not sure exactly what the date of when they were first processed, but I believe that many of these were made about 10 years ago or at minimum 5 years ago. So where a lot of bottom-up emissions inventories for the globe use somewhat outdated information. But you can see generally between emissions inventories, there's 10, 20% differences amongst them. So generally pretty good agreement overall. So here I'm showing the top-down NOx emissions for two cities, Paris and Santiago. They happen to be pilot cities that we're working with. We're working with these local governments. And just comparing these two cities, obviously at different continents. And we can see, if we just focus on the top, we can see Paris in 2006 timeframe had emissions of about 200 gigagrams per year, and that decreased in 2018 to approximately 117. So that's about a 42% decrease over this 12-year timeframe. Contrast that to Santiago, Chile, where there was actually an increase over time from 53 to 79. And this was an increase of about 50%. A couple other noticeable things about these two plots. You can see that, well, the NO2 lifetime is a bit shorter in Paris than in Santiago. The NO2 lifetime is a function of not only the sun angle, but also the other chemicals in the air, as well as the topography and kind of the dominant wind direction. There's the other thing is that there's more measurements in 2006 than 2018. There's a row anomaly. I'm sure a few of you are aware of that, the fact that OMI now has about only half the spatial coverage that it once did. So I've applied this method to 96 cities, but it only worked in 49 cities. And the reason it only worked in 49 cities is for a variety of reasons, but most often it was because there was an influence of other cities' emissions nearby. So for example, Washington, DC, Baltimore is very close by. And so you have two plumes interacting, and it just makes it hard for the statistical method to converge to an answer. So if we take these 10 cities that I'm showing here, which are roughly representative of each continent or regional region of the globe, and let's just focus on the US for a second, which is the top left in Chicago. We can see that generally the emissions inventories are capture pretty well what's going on. I wouldn't glean too much. I wouldn't take too much out of the fact that the purple is a little bit higher than the emissions than the emissions inventories. So the purple is OMI. Sorry, I didn't say that. Purple is the top-down OMI, and the other colors are the emissions inventories. And so, yeah, I would just look at the percent decreases over time, and in OMI it's about 60%, and the emissions inventory, especially SEDS and Eclipse, also show about 60%. I didn't include Edgar because it doesn't go quite as long in time. Anyway, so Chicago, Paris generally do pretty good, but then once we start to get to some of the Asian countries, China, in Japan, India, and the Middle East, we can see large, I would say large discrepancies between the emissions inventories themselves. I mean, you're seeing factor of 2, sometimes factor of 3 differences between the emissions inventories in these locations. For Wuhan, this is pre-pandemic. We can see that there was a peak in about 2011, 2012 with a decrease thereafter. And most of the emissions inventories capture this decline over time, but it varies in the magnitude quite significantly. If we go down to Delhi, which is the 4th column, bottom row, we can see that the top-down emissions are quite a bit lower than what the emissions inventories are showing. And I think that's actually mostly due to the satellite measurement, the aerosol effects on the satellite measurement. But even still, we can see a very large discrepancy between the emissions inventories themselves. So that's really what I'm trying to shine a little bit of light on, is that the emissions inventories, especially in Asia, can have quite a big difference between themselves. And it's still unclear which is best, but I'll show later that this, actually the next slide, that the SEDS is probably the best of the 4. So when I sum up against all 49 cities that I've done this method for, that's what I'm showing in this panel here, is approximately a little less than 10% of the total global NOx emissions. Remember, total global NOx is about 100 teragrams. Here for these, I'm showing 6 to 8 teragrams. But so the real takeaway I want to leave you with here is the difference in the trends over time. And so OMI is, amongst these 49 cities, OMI is suggesting a 30% decrease, a 32% decrease over this 12-year period, whereas the bottom-up emissions inventories really don't seem to capture the same decrease over time. They capture a decrease of about 10 to 15%, but not the same decrease of 30% from the satellite. And so that's really one of the takeaways. And the main reason I say that is because there's a lot of uncertainties with the actual magnitude of emissions. And I'm not going to go through every single one of them, but the total uncertainty of the magnitude is on the order of 50 to maybe even close to 60%. But the uncertainty of the trend is significantly less than that. And so that's really what I want to focus on the trend here. Now going back to the United States, I've taken a closer look at OMI compared to the NEI, and generally there's pretty good agreement over time. I mean, again, you can see some magnitude differences, especially in New York City and Chicago, but generally in the more recent years, pretty good agreement. I'd say the one thing that there is, I would say, a disagreement is the kink in the 2009-2010 timeframe, where the EPA NEI inventory just shows it's a constant decrease over time, but we know that there was a recession. And this actually shows up pretty well, especially in New York City and Chicago, where there's a pretty sharp decrease between 2009 and 2010. And again, I think that this is very real. And actually, I just want one more side comment here, is that one reason I think that there's so much variation from city to city is because the input data is provided by the states themselves. So, for example, California might provide does provide different data than New York City, but also California, for example, might provide better data than New York City. So it's really important to realize that the NEI is based on state reported data, and therefore you can have, if you have good agreement in one particular state, that doesn't mean that there's going to be a great agreement in a different state. All right, so now actually almost all of the images I showed previously were OMI images, and now I'm going to focus now on TROPOMI for the rest of the presentation. And here I'm on the left column, I'm showing TROPOMI, and the right is OMI. On the top row, we have an annual average of 2019. Both are taking full measurements during that year. And we can see that OMI is very clearly larger than TROPOMI during this coincident time frame. But on the other hand, TROPOMI has significantly better resolution and much better sensitivity. And we can start to pick out very small point sources in the TROPOMI plot, but you can't do that in OMI plot. If you go down to the bottom row, and we can just see the very big difference in spatial coverage on a day-to-day basis between TROPOMI and OMI. This was a fairly sunny day across the continental United States. And TROPOMI was able to get a measurement in a lot of different areas and can pick up the cities, Chicago, New York City, Los Angeles, San Diego very, very well, but that cannot, I mean, actually none of those cities, with the exception of Chicago, really, can you pick up a plume on an individual day. So going through kind of the same type of setup here, how does TROPOMI compare in the presence of power plants? Well, it compares very well. I'm not going to get into this in too much detail, just to say that that the operational product does, again, have a low bias in polluted areas, and there's a couple papers on this. I encourage you to check them out. But when you use a research grade product, this one's from Environment Canada, you get excellent agreement between what the power plants are showing or what are measuring at the stack and these top-down emissions. In the paper that I published now 2 years ago, I also used that to estimate the emissions from these 3 largest cities. I know I'm talking lots of different methods about some of the same cities, but really the takeaway here is that the NEI generally is pretty good within some uncertainty. For New York City, there's some evidence, maybe not conclusively, but some evidence maybe that the emissions are overestimated in New York City and just a little bit of an underestimate in Toronto, but Chicago is pretty good. But really what's amazing about TROPOMI is the fact that you can use it for single day snapshots. And so here's an example from Chicago. We actually had easterly winds on this particular day. It's not normal, but what's nice about that is that there were no clouds, and you can see a very nice plume decay downwind. So from the east to the west. And then rotate this and then calculate your top-down NOx emissions. This is actually a Saturday, so if you're following along, the top-down NOx emissions were, I'll just go back for convenience. Top-down NOx emissions were about 165 for all days, but on this Saturday, it was about 30 to 40% lower. So it's exciting that we can use it for a single day. And for the last 2 or 3 minutes here, I just want to discuss some very preliminary work I've done using NOx to CO2 ratios to estimate CO2 emissions from NOx emissions. And so here I'm just using the reported NOx to CO2 ratios as reported by the EPA. In 2005, the NOx to CO2 ratio was larger than in 2017. This is shouldn't be a surprise to everyone, and this is due to controls on NOx, but not necessarily on CO2. And we can also see the locations of the power plants where they have significantly lower NOx to CO2 ratios, and that's because they have controls on the stack themselves, whereas cars and trucks, et cetera, they generally have a larger NOx to CO2 ratio. And it's also interesting to see that the NOx to CO2 ratio is smaller in states that have that are controlling for ozone. For example, New York, Texas, and California have lower NOx to CO2 ratios than, say, Montana or Kansas, where they don't have any. They don't have an ozone problem, as far as I know. So the discontinuities at the state borders are actually due to the artifact of the state-by-state inventories which were used. But just most importantly, I verified, I won't say verified, but I compared this to top-down CO2 emissions from the TCON and the OCO2. This is from a paper from Hedgelis. I didn't put the reference here, but I'm sure you can find it. Yeah, so we can see that during this time from 2006 to 2017 timeframe showing here, there's about a 23% decrease in CO2. The emissions inventory actually only showed a 7% decrease. The big assumption here is that the NOx to CO2 ratio is approximately correct. That's an assumption, but it's something that we want to look into further. But even still, it shows that using NOx to infer CO2 does a pretty good job. And that's what I'm showing in the 2015 timeframe. So this is very preliminary type of methodology, but I think there's some power in using NOx emissions to estimate CO2 emissions from cities. So with that, I'll just wrap it up. I've actually gone through these conclusions already, so I'll actually fast forward through a few of these. So yeah, the key takeaway from the first part is that that tropospheric vertical column measurements need model information. The tropospheric vertical column measurements generally have a little bit of a low bias, but this can be remediated using a regional air mass factor. And then I showed that globally, urban NOx appears to be dropping faster than in reported emissions inventories. I think actually this is, from what I'm seeing, it has to do, especially with the NOx emissions reductions in China, are really exceeding what are projected by some inventories. So this is really a great news story, because this means that cities have a lot of power to control both the air quality, but also greenhouse gas emissions. And then finally, TROPOMI measurements truly are revolutionary. I've used this for some of the COVID work that I haven't discussed at all, but you can check out the video if you have the PDF version. And then finally, I've set a foundation to infer CO2 from NOx emissions, top-down NOx emissions. I do just want to highlight again that there are a lot of uncertainties with this methodology, but as I keep working on this, as the community keeps working on this, hopefully these uncertainties will become a little bit lower over time. So, but the key takeaway really is that even though there's uncertainties with the magnitude, the uncertainties of the trends are quite a bit smaller. And so that's really where you want to use satellite data, is in quantifying trends over time. So with that, I want to thank all of the colleagues that have helped me with all of these projects. I went through quite a few papers and publications, especially David Streets and Susan Annenberg, who provided most of the funding for this work, but also just all the postdocs and mentors and co-authors. I'm very happy that they were able to contribute, and very grateful for all their knowledge and expertise. So with that, I want to thank you for your attention. I hope you enjoyed this, and I'm happy to take questions. Thanks.
Okay, great. Thanks, Dan. So we'll switch over to Slido. Thanks. And it'll take a little bit for the questions to percolate through. So while we are waiting, I'll just ask something that's been on my mind here is, have you looked at sort of a breakdown of, or has anyone looked at sort of a breakdown of meteorological conditions when retrievals are especially bad? And I'm not even necessarily thinking when the winds are strong, because if they're sort of strong all day, you might think that, that sort of has a constant effect. I'm actually wondering if the weather's really variable in an area, like you get big shifts in weather, a front goes through, can that drive a big disagreement between the sort of top down and bottom up, unless they're perfectly simultaneously occurring?
Yeah, that's a good question. I actually discussed this in my COVID work a little bit, but I'll answer that question. So yeah, the ideal in an ideal situation, you want to average over many months worth of data. And so I think the kind of the rule of thumb is that if you have about 3 months worth of data, at least of the TROPOMI data, that more or less averages out some of the meteorological concerns. Ideally, if you can, 6 months. In some of, yeah, and that's why in most of the work that I showed here, I use longer term averages. With that said, for my COVID work, it was important to know what NO2 was on a week by week basis, and so that's what essentially I tried to normalize for that. And so on a day with very I guess large winds or very windy days, the NO2 concentrations would be smaller, but on very stagnant days, the NO2 concentrations would be much larger. So I essentially was able to normalize to just a medium windy day, or I think it was about 3 meters per second winds. And you could, it's just a simple scaling factor. And I did that for a variety of things. Also, like the day of week, also it's on meteorology, but that's something that varies from day to day. What was I'm forgetting, but yeah, and with both wind speed and direction. So wind speed and direction are really the key things, because of course when there are clouds, there's no retrieval. So that's not something in particular I have to worry about, but there has been other people that have looked at what's called the clear sky bias, and that's something that I'm interested in looking at further. That was long-winded. Hopefully that answered.
Oh, that's great. So we've at least got one question in Slido. Easiest way is probably if you sort of read it and then answer it. Although if you want me to intervene, you can just let me.
Okay, sure. So I believe from Ivan. So you clearly show the effects and implication of the NO2 profile shape. The aerosol extinction profile may also have an effect on the estimation of the air mass factor. Could you please mention if the aerosol load is taken into account in the estimation of the air mass factor? So the short answer is yes, it is. This is in the radiative transfer model, but essentially, it gets complicated quickly, because generally what at least the NASA OMI team has suggested is that on days with very heavy aerosols, those are essentially interpreted as clouds and screened out. And so on days with just a very small amount of aerosols, then this effect won't have much of a role. There are ways to kind of rerun the radiative transfer model to explicitly account for aerosols. At least the NASA OMI NO2 product does this implicitly, which is what I just mentioned, but you can do it explicitly. For some place like Seoul, Korea, and China, this matters quite a bit. And there's a Peking, I believe, Peking TROPOMI NO2 product and Peking OMI NO2 product, and those are great for China. But for the United States, in the absence of wildfires, I'm not even going to discuss wildfires. Maybe that's what this was in response to. But in the absence of wildfires, there's not necessarily a need to account for aerosols all that much here. But it can be done. That's not really my expertise or my focus is.
We can wait a little bit to see if another question trickles in. Usually there's a little bit of a delay from going through moderation and then just getting folks to type things out. So we'll give it another minute just to see if anyone else has any burning questions. Everyone remember, just submit through Slido beneath the main seminar window. Okay, if there are no other questions, I'll sort of drag this out a little bit longer, but if there are no other questions, I want to thank Dan for giving us the seminar today. We appreciate your time, and thanks for sharing with us this information. I think it's actually, this was good because you know, we're moving to really take advantage of these new geostationary satellites, and it's good to know some of the amazing details and information that can be extracted from them. So we really appreciate it. For everyone else viewing at home, please thank Dan as you can in your own way virtually, and check your email today for another announcement for next week's seminar. We've got some coming back to back. Okay, everyone. Thank you. Have a good afternoon.
Thank you, everyone, for attending.